Section: Introduction. In this section, we discuss how large language models, LLMs, despite their impressive capabilities across various tasks, encounter a significant limitation due to their restricted context window size. For instance, models like Llama 2 can only process up to 4,096 tokens at a time. When we try to make these models understand or remember information beyond this limit, their performance drops because they haven't been trained to handle more positions. This limitation becomes a real problem when we want to use these models for tasks that require learning from a lot of examples at once or when deploying them as interactive agents. Recent studies have shown that it's possible to train these models to handle longer texts, up to around 128,000 tokens, by fine-tuning them on such texts. However, trying to push this boundary further faces three major challenges. First, adding many new positions that the model hasn't seen before can introduce errors and make the model's predictions less reliable, especially when we're talking about expanding from 4,000 to more than 1 million tokens, which means over 90% of the positions are new to the model. Second, to fine-tune the models for longer texts, we need long texts, but such texts are rare, especially those longer than 1 million tokens. Plus, training on these long texts requires a lot of computing power and resources. Third, when we make the context window very large, the model's attention gets spread too thin over many tokens, which can hurt its performance on tasks that originally required a shorter context. To overcome the first challenge, some approaches have been tried, like adjusting the model's understanding of position within a text to fit the new, longer context without losing the essence of the original training. This involves tweaking the model's positional embeddings, which help it understand where each word is in the text. Some methods have tried to adjust these embeddings in various ways, but they haven't fully taken advantage of the complex patterns in how information is spread across different positions in the text. This oversight leads to a loss of information and restricts how much we can extend the context window. Our research has led to two important discoveries. First, we found that when adjusting the model's positional embeddings, it's crucial to consider how these adjustments vary across different dimensions of the embeddings and across different positions in the text. For example, the beginning of the text and certain aspects of the embeddings are more sensitive and require less adjustment. The best way to adjust these embeddings depends on how much longer we're trying to make the context window. Second, by paying attention to these nuances, we can better preserve the original information in the embeddings, especially for the most critical dimensions and positions. This approach minimizes the loss of information and provides a stronger starting point for further fine-tuning. It even allows us to extend the context window by up to 8 times without any fine-tuning in some cases. Inspired by these insights, we developed LongRoPE, a new method that significantly extends the context window of LLMs beyond 2 million tokens. LongRoPE is innovative in 3 main ways. First, it carefully adjusts the model's positional embeddings by considering the different sensitivities across the embedding's dimensions and the text's positions. To find the best adjustments, we use an evolutionary search algorithm that's efficient even as the search space grows very large. Second, LongRoPE uses a step-by-step approach to extend the context window, starting with a smaller extension and then gradually increasing it. This method doesn't require directly training on extremely long texts, which are hard to find and expensive to process. Finally, to ensure that extending the context window doesn't hurt the model's performance on shorter texts, LongRoPE fine-tunes the adjustments for different context sizes. We tested LongRoPE across various LLMs and tasks that require understanding long texts. Our results show that LongRoPE maintains high accuracy and low error rates even as the context window grows from 4,000 to 2,048,000 tokens. It achieves over 90% accuracy in retrieving information from long texts and performs comparably to standard benchmarks within the original 4,096 token window. LongRoPE can be applied to any LLM that uses rotational position embeddings, and we plan to make our code and models available for others to use. In summary, by addressing the challenges of extending the context window of LLMs, we've developed a method that significantly enhances their ability to understand and remember information from much longer texts. This breakthrough opens up new possibilities for using LLMs in a wide range of applications. Section Summary. In this section, we explore the challenges of extending the context window for large language models, LLMs, beyond the typical limits, such as Llama 2's 4096 token constraint. We introduce LongRoPE, a method that effectively extends the LLM context window to over 2 million tokens by leveraging non-uniform positional interpolation. By considering multidimensional non-uniformities in positional interpolation, LongRoPE achieves a 2048K context window without the need for direct fine-tuning on extremely long texts, demonstrating improved performance on long context tasks across various LLMs. Section: Preliminary. In this section, we delve into the preliminary aspects of our research, focusing on the necessity of positional information in transformer models. Specifically, we explore the LongRoPE position embedding, a method that has gained popularity in recent large language models, LLMs. To put it simply, for any given word or token in a sequence, its position is represented by a unique encoding. This encoding is determined by the token's position in the sequence, the dimension of the embedding, and a specific rotary angle, which is based on a predefined rotation frequency. The base value for calculating these frequencies is typically set at 10,000. We also discuss the concept of extending the context window, which is crucial for understanding larger chunks of text. The extension ratio, denoted as S, is the proportion of the new, extended context length to the original length. To adjust the context window, we look at different methods of positional interpolation, which involve modifying the rotation frequencies based on this extension ratio. One such method is linear positional interpolation, pi, which linearly adjusts the position indices within a certain limit. However, this approach tends to compress position information too much, making it difficult for the model to differentiate between tokens that are close together. This becomes particularly problematic at higher extension ratios. Another approach is based on the neural tangent kernel, NTK, theory, which views LongRoPE from an information encoding perspective. This method distributes the interpolation pressure differently across the LongRoPE dimensions, scaling down the frequencies less for lower dimensions and more for higher dimensions. This results in a more balanced distribution of position information, addressing the issue of crowded positions seen in pi. Yarn, another significant advancement, categorizes LongRoPE dimensions into 3 groups based on their frequencies, applying different interpolation strategies to each. This method, however, relies on empirical experiments, which may not always yield optimal results for new LLMs. Inspired by the NTK and Yarn methods, we noticed the benefits of applying nonlinear approaches to positional interpolation, especially when considering the varying frequencies across LongRoPE dimensions. However, these methods often depend on manually set rules, leading us to question whether there are more optimal, yet undiscovered, nonlinear approaches. To explore this, we employed evolution search to find better non-uniform positional interpolations for a specific model, guided by performance metrics on a validation set. Our empirical analysis revealed significant findings. Firstly, we discovered that LongRoPE dimensions exhibit substantial non-uniformities, which are not effectively addressed by current interpolation methods. Our approach, which involves searching for the optimal rescale factor for each dimension, showed considerable improvements in model performance without the need for fine-tuning. Secondly, we found that for the initial tokens in a sequence, less interpolation should be applied, as these tokens play a crucial role in the attention mechanism. Our experiments confirmed that maintaining the original position encoding for the first few tokens improves performance, with the optimal number of tokens varying depending on the target extension length. Lastly, we demonstrated that non-uniform positional interpolation not only enhances performance in non-fine-tuning scenarios but also provides a solid foundation for further fine-tuning, as evidenced by our results with a significantly extended context window. In summary, Our study highlights the importance of considering non-uniformities in both rope dimensions and token positions. By effectively utilizing these non-uniformities in our positional interpolation approach, we significantly improve the ability of LLMs to extend their context window, thereby enhancing their overall performance. Section Summary. In this section, we focus on rope position embedding for transformer models, which simplifies the encoding of token positions using rotation frequencies. We introduce non-uniform positional interpolation methods inspired by NTK and yarn, showing significant improvements in extending context windows for LLMs without the need for fine-tuning, especially in handling varying rope dimensions and token positions effectively. Section LongRoPE. In this section, we introduce LongRoPE, a method inspired by our discoveries. We developed LongRoPE with an efficient search algorithm that takes full advantage of two specific irregularities in data. By doing so, it allows us to expand the context window of large language models, LLMs, to over 2 million tokens. When we talk about the problem we're trying to solve, these two irregularities create a huge range of possible solutions, making it tricky to find the best one. To tackle this, we treat the problem like a search challenge. Imagine we have a LLM that needs to understand a document longer than its maximum token limit, which we'll call L. Each piece of the document, or token, has a specific position. Originally, the position of a token in the document affects its meaning through something called a rotary angle, which changes based on the token's position and the dimension we're looking at. To find a solution, we introduce a set of factors that adjust these rotary angles to handle the irregularities. These factors change the angle for tokens beyond a certain position in the document. For the initial positions, we don't change anything. But for positions beyond a certain point, we apply these factors. Our goal is to find the best set of these adjustment factors for each dimension of the rotary position encoding. This way, the LLM can better predict the next token in the document, minimizing errors, which we measure using something called perplexity. To find these optimal adjustment factors, we designed a large search space that considers both types of irregularities. We simplified our search by looking for two main things: the adjustment factor for each dimension and the position threshold from where to start applying these factors. We allowed a range of values for these factors and thresholds to find the best combination. Given the vast number of possible combinations, we used an evolutionary search strategy to efficiently explore the search space. We started with a mix of predefined and randomly mutated factors as our initial population. To make our search smarter, we only considered new sets of factors that followed a rule. Each factor must be equal to or larger than the one before it. This rule is based on the idea that different dimensions of the data need different levels of adjustment. Our evolutionary search was quite effective. It allowed us to significantly extend the context window of a model called Llama 2 from 4,000 to 32,000 tokens without needing to fine-tune the model. This is a big deal because other methods we compared with, like Pi and some non-uniform approaches, didn't perform as well when we tried to double the context window size. In summary, our LongRoPE method uses a smart search strategy to find the best way to adjust the rotary position encoding in LLMs. This lets us handle longer documents by expanding the context window far beyond what was previously possible, all while keeping the model's performance strong. Section Summary. In this section, we introduce LongRoPE, a method that addresses the complexities arising from non-uniformities in position embedding optimization for large language models, LLMs. By formulating the multidimensional non-uniform position interpolation optimization problem as a search problem, we aim to find optimal rescale factors to extend the context window of LLMs beyond 2 million tokens, achieving minimal next token prediction loss. Our evolutionary search approach efficiently identifies non-uniform rope rescale factors, enabling significant context window extensions without fine-tuning, outperforming existing methods like Pi, NTK, and yarn. Section: Extending LLM context window to 2048K. In this section, we discuss our approach to significantly increase the context window of pre-trained large language models, LLMs, from the usual 4K to an impressive 2048K. We've found that our unique method of non-uniform positional interpolation allows us to expand the context window by up to 8 times without the need for fine-tuning. However, for more substantial expansions, specifically up to 512 times, fine-tuning becomes essential. One strategy involves searching for rescaled factors suitable for the rotational positional encoding, LongRoPE, under the desired 2048K size before fine-tuning. This approach, however, is hindered by the high cost of training resources. Additionally, from our experience, fine-tuning LLMs for such a large expansion ratio presents its own set of challenges. Thankfully, our LongRoPE technique proves effective for both the original and the fine-tuned extended LLMs. We introduce a progressive method that allows us to reach our 2048K target with only 1K fine-tuning steps within a 256K training length. Initially, we extend a pre-trained LLM to 256K using LongRoPE search. For instance, with Llama 2, we search for the target context window sizes of 128K and 256K, achieving extension ratios of 32 times and 64 times, respectively. Following this, we fine-tune the pre-trained LLM to reach a context window size of 256K. This involves initially fine-tuning Llama 2 for 400 steps using the LongRoPE rescaled factors for 128K, then updating the LongRoPE rescaled factors to 256K on the finish checkpoint and conducting an additional 600 steps of fine-tuning. This method is more efficient than directly fine-tuning to 256K. Next, we perform a secondary search on the fine-tuned 256K length LLM, which allows us to achieve an extremely large context window size of 2048K without further fine-tuning. The final extension ratio here is 512 times. After extending to such a long 2048K context window, we observed a drop in performance within the original context window. This issue, known to arise from positional interpolation, results from forcing position embedding in higher dimensions within the original context window into a much narrower space, which negatively impacts the model's performance. To address this, we conduct an additional evolution search on the extended LLM to adjust the LongRoPE rescale factors for shorter context lengths, such as 4K and 8K, reducing the maximum allowed searched lambda due to the lesser positional interpolation required for shorter lengths. During inference, the LLM dynamically adjusts the corresponding LongRoPE rescale factors. For our evaluation setup, we apply LongRoPE on Llama 2 to 7B and Mistral 7B, assessing performance based on perplexity of extended context LLMs on long documents, a passkey retrieval task that evaluates a model's ability to distinguish relevant information from a vast amount of irrelevant text, and standard LLM benchmarks within a short 4096 context window size. Regarding fine-tuning, for Llama 2, we employ a learning rate of 2E5 with linear decay and a global batch size of 32. We fine-tune for 400 steps on the Red Pajama dataset, segmented into 128K pieces, each starting and ending with specific tokens. Then, using the completed checkpoint, we proceed with an additional 600 steps to achieve a 256K context window. The 128K context size training utilizes 8 A100 GPUs, while the 256K training requires 16 A100 GPUs. For Mistral, we use a constant learning rate of 1E6 and a global batch size of 64, following the yarn setting for both 128K and 256K models, with 400 steps on the Together computer's long data collections using a 16K sequence length, trained on 4 A100 GPS. In our search for the target window size within 256K, we employ specific parameters and select the top 32 for mutation crossover in each iteration. Perplexity is calculated using samples from the PG19 validation set for shorter windows and from the Pilebooks 3 validation set for windows over 512K. Finally, to achieve the 2048K context window, we fine-tuned models with 128K and 256K context windows, resulting in LongRoPE 2048K models for both Llama 2 and Mistral. We compare these models against state-of-the-art context window extension baselines, including various open-sourced LLMs fine-tuned after positional interpolation. Section Summary. In this section, we introduce a method to extend the context window of pre-trained LLMs from the traditional 4K to over 2048K using non-uniform positional interpolation, achieving an 8 times extension without fine-tuning. For larger extensions, fine-tuning is necessary, and we propose an efficient, progressive method that achieves the target 2048K with just 1K fine-tuning steps within a 256K training length. Additionally, we address the performance drop within the original context window after extending to 2048K by adjusting LongRoPE rescale factors for shorter context lengths, such as 4K and 8K, to mitigate the negative impact on the language model's performance. Section: Main Results. In this section, we delve into the main results of our study on long-sequence language modeling, particularly focusing on sequences up to 256,000 tokens in length. We start by comparing our models with the latest state-of-the-art large language models, LLMs, using two different datasets, PROOF-LE and PG19, to showcase our model's versatility. To assess the model's performance, we measure perplexity, a way to gauge how well a model predicts a sample, across various context lengths using a sliding window technique. For the PG19 dataset, we evaluate our models across the entire test split, which includes 100 documents. In the case of PROOF-LE, we select 10 samples at random, ensuring each has a length of at least 128,000 tokens. Our findings reveal two important points. Firstly, our enhanced models demonstrate a consistent decrease in perplexity as the evaluation length increases from 4,000 to 256,000 tokens, indicating their improved ability to utilize longer contexts. Secondly, even when the context window is expanded 16 times, a scenario typically challenging for maintaining performance, our LongRoPE 2048K models surpass the performance of leading baseline models within a 256,000 token context. Moving beyond the 2 million token mark, we use the Books 3 dataset to test our models on extremely long documents. For practicality, we randomly select 20 books, each exceeding 2,048,000 tokens in length, and apply a 256,000 token sliding window for evaluation. The results show that our LongRoPE method successfully extends the context window of Llama 2 to 7B and Mistral 7B models to 2,048,000 tokens, achieving perplexity scores that are on par with or better than those of the baselines for shorter lengths ranging from 8,000 to 128,000 tokens. We also explore the performance of our models in a passkey retrieval task, where the model is tasked with finding a hidden 5-digit number within a long document. Despite the daunting challenge of locating a specific sequence within a document containing millions of tokens, our LongRoPE Llama 2-2048K model maintains high retrieval accuracy, from 90% and above, across all tested lengths up to 2,048,000 tokens. The LongRoPE Mistral 2048K model keeps a perfect accuracy rate up to 1,800,000 tokens, with a slight drop at 2,048,000 tokens, which aligns with our expectations based on the observed perplexity trends. Furthermore, we evaluate our LongRoPE 2048K models on standard benchmarks within their original context windows, using settings like zero-shot and few-shot on various tasks. Our models achieve results comparable to the original benchmarks and even surpass the original Mistral model on the truthful QA task by 0.5%. In the ablation results, we examine the effectiveness of our second positional interpolation strategy, which involves a non-uniform adjustment to the model's positional encoding. This strategy proves to maintain a consistent level of perplexity across extended lengths, contrasting with the rapid increase in perplexity observed with other interpolation methods. Additionally, we demonstrate a significant improvement in performance at shorter context lengths by adjusting the LongRoPE factors, highlighting the importance of our approach in maintaining model efficiency across a wide range of document lengths. Lastly, we analyze the impact of non-uniformities in both the LongRoPE dimension and token position on model performance. Our experiments show that non-uniformity in the LongRoPE dimension significantly reduces perplexity, especially at shorter lengths of 16,000 and 32,000 tokens. However, the benefits of non-uniformity in token position become less pronounced at extremely long lengths, such as 2,048,000 tokens, suggesting areas for future research. Section Summary. In this section, we compare the performance of extended long-sequence language models, LLMs, within a 256K evaluation length using datasets like PROOF-LE and PG19. We observe that our extended models exhibit decreasing perplexity trends from 4K to 256K evaluation lengths, showcasing their ability to leverage longer contexts effectively. Additionally, our LongRoPE 2048K models outperform existing baselines within 256K context length, even when faced with a context window 16 times longer, demonstrating superior performance in maintaining accuracy over longer sequences. Section: Related works. In this section, we delve into various methods related to our work, highlighting the differences and similarities among them. We explore not only position interpolation-based methods but also other innovative approaches. One such approach involves retrieval-based methods, which incorporate an external memory module. This module is tasked with storing extensive past contexts and includes retrieval modules for fetching related documents during inference. These methods typically require significant changes to the architecture of large language models, LLMs. In contrast, our approach is more streamlined, requiring only minor adjustments to positional embeddings. This allows us to tackle a broader range of tasks that involve long contexts, such as summarizing lengthy documents and performing few-shot learning. Additionally, we examine attention-based context window extensions. Unlike the straightforward interpolation of positional embeddings, some researchers have extended the input context capacity of the original LLMs by tweaking the attention mechanisms. The central strategy here is to introduce novel attention masks that prevent the overwhelming surge of attention signals caused by adding new positions. These techniques, along with positional interpolation methods, are seen as complementary to each other. Another area we look into involves fine-tuning-based approaches. These strategies concentrate on how to efficiently adapt pre-trained LLMs with altered position embeddings to accommodate longer contexts. Examples include Code Llama, Llama 2 Long, and Scaled ROPE, which all opt for a significantly large base value for LongRoPE and then fine-tune the model for the desired length. Our method stands out by offering the flexibility to work with various target lengths and the capability to handle contexts extending beyond 2 million characters. More recently, the challenge of fine-tuning for extremely long contexts, specifically those exceeding 128,000 characters, has been acknowledged due to the substantial demand for GPU resources. To address this, solutions like LongLoRA and POSE have been introduced to reduce this computational burden. Our approach is designed to complement these efficient fine-tuning methods, providing a versatile solution to the challenge of processing long contexts in LLMs.